So we'll see if I get that done by tomorrow. I like to most only hold on to a week, so I think I'm behind that. So tomorrow we have a lab, and then the following Thursday you have your first unit exam in here. Right. Okay, so we're ready for this, right? Okay. So actually there's an assignment slide in part 11, and that's where we're going to actually break away from part 11 and pick up part 12. So it kind of, if you're into kind of, well, what are we going to do? Well, then we're going to do some of part 12, because actually that talks about freezing point depression, which is what your lab is tomorrow. But so is vapor pressure lowering as part of freezing point depression. It's all kind of together. So it should work out fine. What it means for us is that on Friday then we'll pick up the end of part 12, come back and pick up two volatile solute in part 11, and then for Monday and Wednesday we'll be ready for unit 2 stuff. So that's kind of how we're going to do it. So do you remember when we talked about state function and independent of path versus a path-dependent function? Okay, that term has nothing to do with colligative properties, other than it's just kind of a broad, overarching thing that applies to stuff in chemistry, stuff in physical science. So a colligative property sounds so bizarre. A colligative property is independent, depends only on amount, does not depend upon what it is. Colligative property, and it's kind of, I was thinking today, it's more of a physical phenomenon. Actually, you're going to see that here in a minute when I talk about vapor pressure lowering. It's a physical phenomenon, not a chemical phenomenon. And to me, that's kind of at the crux of why it depends only upon amount, not upon what it is causing the effect. Okay. So colligative properties, one that depends only on amount, not on really the identity of the species. So we've been talking about equilibrium vapor pressures, and we're going to pull up the equilibrium vapor pressure curve here in a minute. But what happens basically when you add a solute like salt or sugar, or it could be sand, it's hard to dissolve sand, but when you add a solute to a liquid solvent, and the liquid solvent needs to be somewhat volatile, then basically the equilibrium vapor pressure will be lowered. And I'll kind of show you why that is. You might even, well, that makes sense, but it is. Okay? As compared to the pure substance. So I like this little video.
Sometimes it's something you say, and sometimes it makes me think of something like.
Oh. Yeah. Oh, goodness.
I don't either, basically.
So you recognize these phase diagrams. So along the x-axis we have temperature, along the y-axis we have pressure, and you kind of see the 3 sectors. We have solid, liquid, and gas, basically. Okay, we've talked about those, the triple point and all that. Now actually we have 2 curves, because the blue curve, as it turns out, is the pure stuff. The red curve, now this is greatly exaggerated. The red curve actually is something, the same stuff to which a solute has been added. Okay, so basically it kind of comes down and over. And again, it's greatly exaggerated, but it works for our purposes. So do you see, if you pick an isotherm just means one temperature. And if we focus on this part, that part is our liquid vapor equilibrium. So if we pick this one right here, can you see where this is the pure stuff, and we have lowered the equilibrium vapor pressure of the solution? I should say it's the solution. I should say it is the solvent that has a solute added to it.
And did you say that this does not depend on what the
Right.
solvent and nor the solute is?
It depends on what the solvent is, not the solute. So it depends on what the solvent is, and it's a colligative property, just depending upon the amount of the solute that's been added. I think I'm getting all my S's right today. Okay, so that's equilibrium vapor pressure lowering. Now, tomorrow we're going to be talking about something called freezing point depression, but let's see. What else I got here? Okay, so that was an isotherm. What if we go ahead and pick not the same temperature, but look if we pick the same pressure? Check this out. Over here, at the same pressure, can you see, this is why if you go, no, this isn't right. Yeah, this would be right. This is why if you go in the mountains where you know it's going to boil tend to boil more quickly because the pressure up there is less. This is why you add salt to it. You add salt to your water because check it out. Remember, the pink is the adulterated, or the pink is the solvent to which solute has been added. The presence of your solute at the same pressure, notice what you have to do. You have to jack up the temperature in order for that thing to boil. That's it. Boiling point elevation, affectionately called bpe for boiling point elevation. Yep. And tomorrow, and I'll try to kind of, this is why I want to break away from part 11 and go to part 12 just a little bit. But this over here, oh, did I? Maybe I didn't. Yeah, I guess we're not focusing on the other part. We'll come back to it. Okay. So do you recognize this part of the curve? This is your equilibrium vapor pressure curves. One of the things that drives me nuts about that previous figure and this figure is the colors are reversed. I know. The red one now, but the one on top, that is the pure stuff. And the blue one underneath it, that actually is the equilibrium vapor pressure of the solvent to which a solute, who cares what kind of solute, but a certain amount of solute has been added. Okay, and then that little, let's see what I got here. This happens to be benzene. So you asked, colligative properties are independent of are dependent only on amount of, in this case, solute. But the solvent does count. So actually we're going to see that there are constants dealing with the solvent, in this case benzene. So, all right. So right here, this is actually, we talked about boiling point elevation. In the next part, we're going to actually talk about the delta T. I wish that was a capital T, lowercase t. The change in temperature from the blue, in this case, remember, is the adulterated or the solvent to which a solute has been added. So we can also talk about delta P, and we'll talk about, I can't remember, I think that might be coming up. Okay, delta P is at the same temperature. How has the equilibrium vapor pressure been lowered? Delta P. In this case, 54 millimeters of mercury. All right. So we talked about knots, and I was thinking about this lecture, and I'm here to tell you knots are important. Okay. The delta H knot, that was standard enthalpies at standard conditions, which was 25 degrees Celsius and 1 bar, I think, something like that. The knots here means the pressure, equilibrium vapor pressure of the pure stuff. Okay, so without the knot, it means actually that is the equilibrium vapor pressure of the solvent to which a solute has been added. Okay, so make sure we're all kind of on the same page here. So when we calculate a delta P, like you saw a minute ago, deltas are always final minus initial. And so the way we think of this is that the initial is the pure stuff. So just to make sure we're all on the same page, the initial is the pure stuff, P naught, and then the final is just simply P. And you could go ahead and make a subscript solvent if you want to. When we get going with Raoult's law, sometimes you have to make sure you understand the P naught is the pure stuff, and the P without the naught is the solution. Okay, so any delta is final minus initial, and I like this because this makes sense. Our final is going to be the solution, the equilibrium vapor pressure of the solvent as it is in the solution. The initial is going to be the pure stuff. Makes sense? So be thinking these would be the equilibrium, these would be the vapor pressure lowering that we're experiencing. We just kind of saw them on two curves a little minute ago. So that's kind of nice if you're a visual person. So we're getting ready to set you up for our Raoult's law now. Now, I bet you guys buy this. Say you go ahead and you have a mixture, you have the solvent, and you've added some solute to it. Does this make sense? In the little video we saw that the equilibrium vapor pressure of the solvent in the headspace above will be proportional to the mole fraction of the solvent. Okay, so you have little liquids that have broken their bonds. The mole fraction, the equilibrium vapor pressure that you see here is related to the mole fraction down here. So that's to say that as you add more solute, the mole fraction gets less, and actually you're going to see the equilibrium vapor pressure go down. So we know it's not an equal sign, but it's a proportionality sign symbol that we used when we developed the gas laws. Okay, so we can say the equilibrium vapor pressure of the solvent in solution is proportional to the mole fraction of the solvent. Well, we know we can replace the proportionality symbol with an equal sign if we introduce a constant, and that's what we're going to do. We're going to pull out that proportionality symbol, and we're going to put the constant K for now. And we're actually going to do a little proof, building up to Raoult's law, which is very simple. A little proof to kind of show you what that K, what that value is. Right? So if we assume or recognize, if we start with if somebody told you that the mole fraction of anything is 1, you'd be like, dude, if the mole fraction is 1, that must be a pure substance. Okay, a mole fraction. So if we go with basically the pure solvent, okay, if we go with the pure solvent, mole fraction of solvent is 1, okay, then actually the equilibrium vapor pressure of the solvent would be P naught because it's pure, okay? In that case, in that special case, okay, we can substitute and actually find then that our K, our constant, is the pure stuff. Okay, so K is the pure stuff. So with that in mind now, we come up with Raoult's law, which, like I said, it's an easy one. It just says that the equilibrium vapor pressure of your solvent is equal to the mole fraction of your solvent times the equilibrium vapor pressure of your solvent as it was in its pure state. So let me put it this way, or kind of reinforce this. This right here, you usually get from a table. That is the equilibrium vapor pressure of the solvent if you didn't add anything to it. Okay, at a particular temperature, get it from a table or a graph. Okay, of course we talked about how you get mole fractions of solvent. If you only have two components, that's going to be the moles of your solvent divided by the moles of your solvent plus the moles of your, I'm running out of solute. Okay, we can do that. Not too bad. So a little bit about Raoult's law. It generally applies only to ideal solutions. And remember, we talked about ideal solutions. Those are ones where they're neither endothermic or exothermic. Basically, the energy required to break the bonds is the same as the energy that's going to be released when the new bonds are formed. Okay. The other thing is, actually keep in mind, it will apply to all of the cute little liquid particles that are trying to go from their liquid to their vapor stage. On Friday, we're actually going to take it up a notch and talk about what if you had two relatively volatile components in a mixture. What does that look like? Okay. But with regard to ideal solutions or non-ideal solutions, even if it is not ideal, if it's a dilute solution, it should be pretty good. Okay, so let's assume that we have two components, A and B. The mole fraction then should always add up to, the mole fraction of all the moles should always add up to be equal to 1. So in this case, the number of moles of A plus the number of moles of B is equal to 1. The equilibrium vapor pressure of component A will be equal to its mole fraction times what it was in its pure state. The equilibrium vapor pressure of the component B will be equal to its mole fraction times what it was in its pure state. Okay, so in that headspace, the total pressure is going to be the sum of those two partial pressures. Okay, so let's just focus on two components, and one of them is non-volatile. So something non-volatile like salt, okay, sugar. So it will not tend to want to go from the liquid to the vapor phase. Well, in that case, then if you were to monitor the partial pressure of that particular component, let's say B is your non-volatile component, you're at equilibrium, you're basically going to have 0 up there, okay? And that is true. So let's do one of those. Those are the easiest ones, where basically your solute in lesser amount is non-volatile, okay? It's not going to go into its gaseous phase. So let's work a problem using Raoult's law. Let's see. Trying to decide if I want to make a picture. I might. I think we got time. So here is my system. And looks like the T is equal to 90 degrees. And we are going to add glucose. Now, glucose is sugar. You think probably non-volatile? I think so. So we're going to have 5.00 grams of our non-volatile solute. And we are going to have 100 grams of H2O down here. Now, if we have to get mole fraction of solvent, water is our solvent. If you have to get mole fraction, which you're going to have to, you can do that, right? When we work the problem, it's going to take a little bit. We can take these the mass, the molar mass of water to get to moles. The mass, the molar mass of that to get to moles, okay? We're supposed to come up with the vapor pressure of water now that you add sucrose to it. Well, according to Raoult's law, it looks like this. The vapor pressure of water will be equal to the mole fraction of water times the equilibrium vapor pressure of water at that temperature in its pure state, which we got to get from a table. Sometimes when I work problems, chemistry problems, students are like, now where do I get that number from? Okay, that has to be given to you. Not too bad. So from the table, the P naught for water at that temperature is 525.8 millimeters of mercury. So here we go. So here's the table we got that number from, in case you need to use it for your homework. Raoult's law, in this case solvent is water. Mole fraction of solvent we can get by taking the moles of water, in this case, divided by the moles of water plus the moles of sucrose, glucose, whatever that was, O's. Back to Chem 1, we know that we can go from mass to moles this way. Okay, for water, we take the 100 grams of water times 1 mole over 18.02 grams, the molar mass of water. You need to show that to me. Rounding to 4 significant figures, we've got 5.549 moles of H2O. You'd have to show me coming up with molar mass of glucose, 180.16 grams per mole. So we take the mass of the solute, 5.00 grams, times 1 mole over 80.16 grams. Our grams will cancel, we'll be left with moles. So now we can get to mole fraction. I think when I work these problems, it's interesting how this mole fraction is going to be really high, right? Because, you know, you're going to take this number divided by this number plus this number. I don't know, maybe it's just me.
Did you go
I can. So the moles of C6H12O6 is 0.0278 moles. Now, we go ahead and in the numerator we put 5.549 moles H2O divided by, in the denominator, 5.549 plus 0.0278 moles, total moles of solution. And I'm thinking 4 sig figs. We're allowed 4 sig figs. So the mole fraction of water is 0.9950. Why do we allow ourselves 4 sig figs?
No,
Okay.
I was wondering if you're yourself.
Yeah. Yeah. So that's going to be our first term. And that second term, of course, is going to be what we got from a table. It's 525.8 millimeters of mercury. So we can knock out what the equilibrium vapor pressure of water would be this way. So the pressure of your solvent, or in this case water, will be 0.9950, which is the mole fraction, times 525.8 millimeters of mercury, which is from the table. Rounding to 4 significant figures. And this makes sense, doesn't it? Because it's always equilibrium vapor pressure lowering. So, I mean, if this is 1, mole fraction is 1, then that means it's pure, and you get your stuff back, you know what I'm saying? Otherwise, it's lower, yeah. So, the reduced equilibrium vapor pressure of your solution will be 523.2 millimeters mercury. Pretty good. I can't remember in my notes. We could knock out a delta P, which is final minus initial. So it would be, it would be this one minus this one, which gives us what, a negative delta P. Okay. So the delta P is 523.2 minus 525.8. Kind of a little convention if you want to save some of your hand cramp is to put, if you're doing a subtraction or addition like that, you can put the two things in parentheses and then the units outside. That works great. Rounding according to decimals, we got negative 2.6 millimeters of mercury. If you get a positive value there, then something's gone wrong. That would be our delta P at that temperature. But notice here, well, I don't know if you noticed or not, but we didn't care, we only cared about the moles that was being added to the solution by the glucose. And the reason colligative properties work is that little video we saw with the big red ones and the purple ones that want to escape. It basically, it's a particle thing. Like I said, it's kind of a physical thing. It basically, they're running interference, and we don't care if they're, well, we sort of do care. We'll talk a little about this on Friday. But it's just the number of them that makes a difference. It's kind of weird. Okay, so these will be due on Friday, Fabulous Friday. Let's take a look at these real quick. But we won't get to, this will be the only assignment due Friday. We won't get to the other ones. Okay, so this one, let's see, basically we're adding glucose, the mass, and we're adding it to water. Wait, it doesn't say. Yeah, we're adding it to water. It's very similar to what we did in the problem. Calculate what the equilibrium vapor pressure will be. Oops, come back here. So we just need to use those masses to get to moles and then come up with the mole fraction and then just plug it into Raoult's law. Raoult's law almost has a cooler name than it really is, like a cooler idea. Get to the moles. I think you guys will be fine with that. Get to moles. Again, this is one from like a year ago, so I'm like, oh, I didn't have to do this today. So you can get the mole fraction, and if we multiply that by, it was already given, I looked it up on a table, at 25 degrees Celsius, not 40, but at 25 degrees Celsius, that is the equilibrium vapor pressure of pure water. So that should do it for you. The next one looks like this, where now we're dealing with the solvent methanol, and the solute that the non-volatile solute is urea, and the formula for urea is given up there. I've had students work this before, and they see the CO and they think cobalt. No, that's carbon and oxygen, because of course it's a uppercase O, so it's got to be oxygen. So you'll need the molar mass actually to take that 17 grams to moles. Okay. Now this is a little bit different, because in order to get to the moles of methanol, you're going to have to use the density of methanol, which is given to get to grams, and then use the molar mass of methanol to get from grams to moles. And then you can knock out the mole fraction, and then you're on your way. Okay? The new equilibrium vapor pressure of the solution will be equal to the mole fraction of methanol times the times the equilibrium vapor pressure of methanol in its pure state, which was given. And then last but not least, it's kind of a think about it sort of question, sort of. Don't really have any numbers given here, but we see A and B from left to right. If we call the first one A and the second one B, of course we see a sludge where A is and no sludge where B is. Okay. And so answer a few questions. Which one would you expect to have a greater equilibrium vapor pressure? Okay, assuming that B is unsaturated. The next one is if evaporation occurs, which one of these would have a constant equilibrium vapor pressure? I kind of like that one too. Think about it. And then the last one is which one's going to have the higher boiling point temperature. And that kind of goes back to, remember we said not only do you have equilibrium vapor pressure lowering at the isotherm, but if you take the same pressure, you actually have what we call boiling point elevation. So, okay, so there. So let's take a look at the first part of the next part. Yeah, I'm a little preoccupied with this white stuff. I don't think it's going to get too bad. It's just our daughter's out there on the road somewhere. School's getting out. I texted her, be careful driving. She's like, oh, Mom. Okay. So boiling point elevation, you saw me call it bpe. Okay. And freezing point depression is fpd, in case I forget. Okay. So I have kind of a proof to talk you through an alternate version of Raoult's law. So this is Raoult's law. We said the equilibrium vapor pressure of the solvent to which a solute has been added is equal to its mole fraction of the solvent times what it was is in its pure state. Well, let's just say you have one, and we'll go with a non-volatile solute. And so the mole fraction of the sum of them is equal to 1. We can rearrange that, and we can get the mole fraction of the solvent is equal to 1 minus the mole fraction of the solute. And now what we're going to do is we're going to substitute this quantity in up for the regular Raoult's law. Okay. When we do that, we get something like this, which according to our rules of kind of solving this, we can take this P naught, the equilibrium vapor pressure of the pure solvent, times 1, and also then minus this times that. You can tell I'm not a math teacher. And we get this, okay? Well, we can kind of rearrange some things. Remember that we said delta P is P of the solvent P minus P naught, that's delta P. Okay, so actually we're setting this up to be delta P over here, is equal to, now keep an eye on your subscripts. They have changed. This is the mole fraction of the solute, not the solvent. Okay, so it looks like this. So actually we have another version of Raoult's law, just kind of taking it through a two-component sort of situation, A and B, solvent and solute. So the change, the pressure lowering, the delta P will be equal to negative mole fraction of the solute minus the equilibrium pressure of the solvent. Too many S's in its pure state. Too many S's. Okay, so what we were just talking about is this region right here. This is our delta P. Just to remind you that the higher one is the pure stuff. The lower one underneath it, in this case red, is the stuff, solvent to which a solute has been added. Okay, this is the boiling point elevation right down here. Well, this at 1 atmosphere, which is normal atmospheric pressures, this is, yeah. So it boils, if it's pure, it boils like this. If it's got, in this case, that solute added to it, it boils of this. Okay, so that's your boiling point elevation. Notice, and again, this is kind of exaggerated, but over here we have kind of something else going on. This is actually your freezing point depression. So the way this works is, again, normal freezing point temperatures in its pure state is here. If you add a solute to it, it's here. And I have one sort of, it's not a video, but I have one figure, I think from your textbook, that kind of says, why is the freezing point depressed when you add something to it? And we do it all the time around here. So like, if they're trying to maintain the roads, make it so ice doesn't build up, what they'll do is they'll go out and they'll spray salt or some sort of, might not be sodium chloride, might be calcium chloride. Ash, actually, it's just a colligative property, something to kind of interfere with, basically, in our case, your liquid water molecules getting together. Okay, you add something there and it kind of stops that from happening. So that's freezing point depression. Okay. Can't remember. Oh yeah. So I'm not necessarily going to talk you through how this was derived, but I want you to remember on the previous slide that delta T, that bpe, okay, those two curves. You can actually calculate that change in temperature by taking K as a constant. There are too many, I get frustrated with chemistry. I'm like, dude, could you not come up with a different constant? Because actually, Monday or Wednesday, when we start in the next unit of material, we're going to introduce another K. There's like two more Ks. There's this K, and then there's one for rates, reaction rates, and there's one for equilibria. Don't blame me. Okay. But anyway, this K is what you look up on a table. Now, little m, molality, okay? Molality of what? Molality not of the solvent, but of the solute. So it depends on the molality of the solute. Yes, I know, it's irritating. Yes. Okay, so that's how that works. Delta T, it's always final minus initial. So this would be the temperature at which it boils when it's been adulterated minus the temperature at which it boils in its pure state. Your delta T's, it's always going to be boiling point elevation. So your delta T's are going to, for boiling point, are going to be positive. They're going to be greater than 0. Okay. Now, freezing point depression has a slightly different sort of equation. So that would be on the slide we looked at. That would be these delta T's over here, FPD, freezing point depression. It's got a similar deal to it. Your K, I don't think I finished this thought, but those big Ks that I kind of said was so irritating, these actually you look up on a table, or you're given enough information to calculate them. Those are your constants, your boiling point elevation constant and your freezing point depression constant. And it would be specific for a solvent, even though it's the molality of the solute here. Okay, I know, it's irritating. But freezing point depression, it's gonna freeze at a lower temperature, so when you go ahead and subtract a higher number from a lower number, you're actually gonna have negative delta T's for that. All right. Yeah, so those two constants, they usually look them up on a table, and they are specific, again, for the solvent, because it's independent of what solute it is. Okay. So we saw that the depression is a function of, if we go with that form, a molality of the solute. Not only are there a lot of S's, but they're all SOL, because we have solvent, solute, solution. Okay. So I don't think you probably have this. I just added, it's a different font, I can tell. Just to emphasize what a colligative property is by definition. It depends only on the amount that's present, not, it's a physical thing, not a chemical thing. I'm so excited to have thought of that this year, to kind of emphasize. Because we're all into like chemistry, like what chemical reaction will occur. Well, if it's a colligative property, you can kind of take the chemistry out of it.
Is this supposed to be boiling point, elevation, freezing point?
It is. It is. Boiling point, elevation. Good catch. Freezing point, depression. Very good. Okay. So let's go ahead and, I think can't remember where I'm going to stop. But, so these would be the solvents, okay, and normal boiling point and the freezing, the normal boiling point and the freezing point depressions. Notice that, for instance, phenol is even the, not phenol, nitrobenzene is the most affected by the presence of a solute, okay? And these are for the same substances, the temperature at which they normally boil, that's the third column, and then the last column is the boiling point elevation constants. So units of your constants, whether it's freezing point depression or boiling point elevation, are always going to be temperature per, usually molal. I think it should always be molal. So this last one for units is a really helpful thing. We talked about molality in this unit of material in Chem 2, and we said that molal is moles of solute per kilogram of solvent, right? That's what molal is. Since it's in the denominator, we could actually take that ratio and flip it up, okay? So actually, this right here is the inverse of molality. So that can be helpful. Okay. So the thing about those Ks, those were all positive, which is kind of the way I think it should be. Your delta T's, remember, for your boiling point elevation, your delta T's are going to be positive. Your delta T's for freezing point depression will be negative. So our textbook leaves the positive constants, but especially in the case of freezing point depression constant, but it assigns a negative sign to the formula to calculate delta T. Some books go ahead and for the constant, they assign a negative value, in which case you need to recognize that and basically reel in the negative that's associated with the equation. Okay. So in some books just kind of totally try to get around it and remove and just talk about magnitude of change of the temperature and recognize that if it's freezing point, it's going to be the sign there. There we go. What's the next? All right, thanks. Okay, so looking at freezing point depression. This actually is not the figure I was talking about, but this is showing you that here in its pure state, it freezes at a higher temperature, and there, where it's kind of blobby, I don't like this picture. There where it's kind of blobby, actually this is a mixture. So basically think of the solute as kind of running in interference to the crystallization process. The point here is this whole test tube sees the same temperatures. This temperature is the same as this temperature. But here it's a solid, and here it's a liquid. And then this one is kind of a series of still images. This is the solid in its pure state. And this is the solvent to which a solute has been added. And the degree of precipitation will be less because those new red particles kind of run interference. Okay. I think what we'll do is just kind of stop it right there, because I don't think we have time to. Let me see what that problem is. Sorry. Yeah, let's just go ahead and do this one, because I think this will help tomorrow's lab. It will go better. All right. Here we go. No, let's not. Let's wait. Because I think tomorrow's lab, I think we'll be in good shape.